Alright, howdy y'all. It is I, the Diabolic tutor. And then we're back here for some more exponents, but a lot less exposition and a lot more actually doing just random problems. So basically everything has been covered, the rules have been covered in prior streams. So let's get started. Boy, I don't even have my drawing program up. Alright, give me one moment. There we go. Something doesn't feel quite right. Okay, that's good to go. Alright. So again, we're just here to do exponential problems. This is just going to be one big marathon, I guess. No, not marathon, but just some practice problems. So starting us off, we have 3x minus 1 is equal to 8. So again, just using whatever exponential rules we have at our arsenal, and then we will solve these problems. So this one is pretty okay. We have term with the variable, we have constant, and we have a constant, so just move this over by adding 1 to both sides. So we get 3x is equal to 9. So at this stage, we have a situation where we have mismatched bases. This is base 3 to the power of x, base 9 to the power of 1. So we can manipulate the right-hand side because we know that 9 is just 3 times 2. I'm sorry, 3 times 3. So 9 transforms into 3 times 3, which is 3 squared. And therein we stumble across one of our familiar rules. If you have matching bases, all you need to do is acknowledge that the bases match up, so therefore the exponents must be the same. So solving for the problem, x is equal to 2, and then we are good to go. But make sure we do a quick check. Backplug it in. So is this answer good? We backplug that in. 3 squared is 9, 9 minus 1 is 8, so sounds legit. First problem, and then moving on. I'm not going to keep track of the numbers because I don't know how long I'm going to stream for today. At least for right now. So problem number 2. If I lose track, it's not a particular big deal. I'll just put the numbers on the VOD. So second problem is 3 to the power of x, and then 1 minus x is equal to 3x minus 31. So in this situation, we have everything is pretty much a matching base. We have base 3, and base 3. So we don't need to worry about mismatched bases. This is simply multiplication, so let us multiply same base, summate the exponents. So summating the exponents, we're going to get x plus 1 minus x. The x's will have canceled, so we'll get 3 to the power of 1, resolving this left-hand situation, and then right-hand situation is just copy-paste. And we arrive at the same situation as prior. This is base 3, therefore you drop the base. Drop the bases, the exponents must be equivalent, so we have 1 is equal to x minus 31. Add 31 to both sides, x is equal to 32. And then we're good to go. If you wish, you can double check. It looks kind of annoying to double check, but 32 minus 31 is exponent 1. And then you plug that in there. 3 to the power of 32 times, because remember parenthetical is multiplication, so times 3 to the power of 1 minus 32. These ones will combine to make 1, so answer is consistent. We are good to go. Nice. And we have the next problem. 3 to the power of, it's just a recurring theme of 3's, right? So we have 3 to the power of 2x minus 1 times 9. That should be familiar. There should be some suspicions. We should probably get this to become base 3. And then we have on the right hand side 3 to the power of x minus 1. So standard situation, take a quick survey. Base 3, base 9, base 3, but base 9 can be transformed into base 3's fairly simply. So that's the 9. Copy paste everything else. Alright, well, we have same base here, base 3 multiplied to another base. So we could just summate the exponents, but make sure you distribute that nonsense first. I'm just going to do it right here. So, you know what? Let's cross this out. I'm going to cross it out just for sake of efficiency. I'll rewrite this as 3 to the power of negative 2, but understand that this thing is being multiplied to that thing. So when we multiply that, just summate the exponents again. So it's going to be 2x minus 1 plus negative 2. So in grand total, 2x minus 3. And then that is equal to copy paste the right hand side. Very familiar, right? Same bases, all you need to do is drop the base. So exponent is equivalent to exponent. You probably don't need to write the steps, so let me try to be as efficient as possible. So the top exponents must be the same thing. 2x minus 3 equals x minus 1. So subtract x from both sides, add 3 to both sides. So x is equal to positive 2, and then we are good to go. Next up, we have no longer base 3. And I'm writing these problems very quickly because these are problems I've written many years ago. So, they're still good. Maybe. So we have 4 to the power of 10 squared times 64 cubed times 4 to the power of x. That's very awkward. And then we have times 2 to the power of negative 8. So quick survey. Always take a quick survey. We have base 4, base 64. That should spark some suspicion because, you know, 64 is 8 times 8. Or you could think about it as 4 times 4 times 4. That's very suspicious, right? Then we have base 4, not a coincidence, and we have base 2, which is unfortunately smaller than the other ones, but we can manipulate this. So I'm just going to do it the way I think this is the most efficient in, you know, using my brain. So I'm going to change everything into base 4, not base 2, because everything else is already 4, or this is close enough to 4, and then this one we can transform to base 4. I'll show you exactly what I mean. So distribute this one first. Distributive property of exponent, so we have 4 to the power of 20, and then this one is factorization, so 4 to the power of 3 in the parenthetical. We still have a cubed on the outside. We will have to distribute that momentarily, and then this is already base 4, so copy paste. This one is the funky one. We can tease apart this one. So I'm going to cross this out. We can transform it into 2 to the power of 4 times negative 2. And because this is all positive, there aren't any shenanigans to worry about. We can choose which order we apply the exponents without having to worry about imaginary numbers. So I'm going to slap on the parentheses like this. So again, if you use distributive property of exponents and distribute the negative 2 back in, you get back to 2 to the power of negative 8, which is our original problem. So that's safe to do. Oh wait, I should do it the other way around. I'm sorry. So not 4 times negative 2, but positive 2 times negative 4. So again, the negative 4 times the 2 gives us a negative 8. We can multiply in any order we wish, since there aren't any negative numbers to negative bases to worry about. So keep it like this. This one, 2 squared is 4, right? Copy paste. Outer exponent. So all the exponents have been forced into conformation, into uniformity. So now it's just tedious cleanup. So 3 times 3 is 9. 9 plus 20 is 29. Summate those exponents. Bases are the same thing, so at this point drop the base. And then we have 29 is equivalent to x minus 4. Add 4 to both sides of this upper equation. So x is equal to 33. More 3s. Do we sense a conspiracy of sorts? But regardless, that is done. Next up, we have... No, that problem's too goofy. Let's not do that one. Here's a... Oh, we haven't covered quadratics at this point. Interesting. That's fine. No quadratics at this stage. Let's just do some more random problems. So we have 16x to the power of negative 2, and then that is equal to 2x plus 1. I guess we're taking a step backwards in difficulty. But this is base 16 and this is base 2. Again, you'll start to recognize which ones you can break down into smaller factors to match the other ones. It'll become automatic. Again, when you see stuff like 9s, 81s, 27s, you're probably matching up with base 3. If you see numbers like 4, 64, 32, you are probably matching those with base 2s. For the most part. This problem here, can we do it? We could solve it using logarithms. We're not going to talk about that again. Alright, so base 16, and then this is base 2. We could transform this one. 16 is just 4 times 4, and each 4 is just 2 times 2. So in grand total, we have 2 to the power of 4. Oh, what did I write? 4. The 4 was lingering in the cache. We have 2 to the power of x plus 1. We have successfully matched the bases. We should probably distribute the exponent, but we're going to simultaneously drop the base. So I'm going to incorporate 2 steps into 1. So top exponent is going to be 4x minus 8. And then the right-hand exponent is just copy-paste x plus 1. Simple algebraic situation. So 3x is equal to 9. And what do you know? 3 is equal to x is equal to 3. Yes. I don't know. I like simple numbers for my answers. So we're done with that one. Let's do some goofy nonsense. So we have 2x inside the parenthetical to the power of 8, and that is equal to 100 times 100 times 100 times 100. So this is just a psychological attack. You can see that there are multiple hundreds and a bunch of zeros staring us down in the face, but there's no need to be intimidated because they're all hundreds. They're each of those is 100. You can combine them using our exponential rule. How many hundreds we have? We have 4 of them, so it's 100 to the power of 4. Copy paste the left hand side. At this situation, we have various tools at our disposal. If we had learned application of power exponents to both sides, we can apply one fourth exponent to both sides. But be aware, you will get kind of a messy situation, somewhat. So if you apply the exponent to both sides of the equation, the left-hand exponent becomes 4, and then the right-hand exponent becomes 1. But don't forget, anytime you transition from even powered exponent into odd powered exponent, you have to worry about pluses or minuses. But since this is exponent 4, whatever is negative in here becomes positive, so we can drop the negatives. Fun times, right? So we arrive at this stage. We can use distributive property of exponent. I think that's the best route. Yeah, distributive property of exponent, distribute to each of those. So we have 2 to the power of 4, which is 2 times 2 times 2 times 2. We'll leave it in exponential form. Distribute the 4 exponent to the x. That looks kind of disgusting. And then we have the 100 here. Is that a nice situation? Well, 100 is simply what? 4 times 25? Yes. Is that useful for us? Because this is base 2, this is base 4. So that's awfully suspicious. This is base 5 to the power of 2. So what do we have here? We have base 2, base 2. Why not bring this, or why not divide that from both sides? So divide by 2 squared, divide by 2 squared. If you recall the rule, all you need to do is subtract the exponents. Alright. Where was I going with this particular problem? I don't know. Did I miscopy this problem? Okay, well, that's fine. We can still get the answer at this point. So divide both sides by 2 squared. I feel like I should have done something else. That's okay. So we have 5 squared over 2 squared, like this. And then when you factor out the exponent, we're going to get 5 halves squared for x is x to the power of 4 is equal to 5 halves squared. I have a feeling this is proceeding in the wrong direction, but let me take a quick sweep about what has happened. Yeah, the answer is supposed to be a lot cleaner than this, but where did things go wrong? I think. Yeah, that becomes 1, and then that becomes the 4. We can use distributive property, that is correct. This is correct. Yeah, it feels correct to me. Oh, this is really weird. Okay, well, that's fine. This is not the direction in which I wanted the problem to go. This one was not tested over the years. I literally wrote this tens of minutes prior to starting the stream, so it hasn't been proofread. That's okay, we can still get the answer. It's not going to be the best answer though. So using the same idea we did there, we can apply the half exponent to each side of the equation. So we apply to this side and to that side. So we're going to get x squared, and here's where things can potentially go bad. This is even powered exponent becoming odd powered exponent, so it's going to be e to the power of 1. Should we put plus or minus? We don't need to, since this is even powered exponent, so there's no need to worry about pluses or minuses. So we arrive here. So at this stage, we can take the square root once more on both sides. So x is equal to, now we need to worry about it because this transitions from even powered exponent on the unknown into odd powered. So you have to put plus or minus square root 5 over 2. But don't forget to rationalize, because conventions. Multiply top and bottom inside the fraction bar, inside the radical by 2. So the top simplifies into root 10 and the bottom is over 2. And that should be the answer. And then again, this is doing it the way where we can apply the radical function to both sides, but what if we are not doing that? Let's try to keep it within the rules we've been using. Alright. So let me approach this a different way. and hopefully it's not gonna get all screwed up. So we have again, consolidate the hundreds. It's to the power of 4. The 100 is actually just 10 to the power of 2, is it not? And why are we doing that? Because I have a sneaking suspicion that the exponents were supposed to match up. So problem designer's privilege, right? So we can distribute the exponents. 10 to the power of 8. At this stage, since this exponent matches that exponent, we can conclude that this one must be equal to this one. But the caveat, because even-powered exponents can cause shenanigans. So first, we acknowledge that it could be positive inside this parenthetical, or it can be negative inside the parenthetical, because again, it's a unknown value getting squared, getting raised to an even power, so the negatives could be obliterated. So keep track of that. So once we acknowledge that, it is 2 absolute value of x. Again, we're considering that it could be positive or negative. So 2 times absolute value of x is equal to 10, because again, the exponents match up. So here we are, divide by 2 is equal to 5. This seems to disagree with the prior answer, but I feel that this one is the better of the two. So that should be the answer. That's weird. Well, I trust in this answer more, so I didn't really goof up the problem. You know what, let's check the alt strat. So again, the alt strat was to apply 4th root to both sides first. You know, I should have factored this in the prior situation, but that's okay. So let's apply the 4th root to both sides. I just want to check to make sure that the methods are consistent, or report consistent answers. Again, 1/4 of 8 is 2, and then 1/4 of 4th is 1. Oh, we could have just taken the square root of both sides, right? Wait, is that what happened? I think I put a 4 up here, right? Yeah, I think for the first run through of this problem, I think I miswrote a 4 here. It's supposed to be only a 2. Yeah. Okay, well, I think that makes a lot more sense. So this one is 10 to the power of 2, so we're basically using the same idea as this. This exponent is congruent with that exponent, but again, we're applying the different strat at this point, so we can raise both sides to half exponent to clear this one with this, this one with this. But remember, we are transitioning from even powered to odd powered, so you have to put absolute value. Well, this color is awful to look at. That's okay. So we have here, so 2x is equal to absolute value of 2x. This is a constant. We don't have to worry about plus or minus with that one, so drag it out as what I did automatically right there. So divide by 2. Well, x is therefore plus or minus 5. And now it's consistent. So again, I think what happened before was I goofed up the 1/4 times 8 and I put like a 4, I think. But should be the answer. Alright. Good to go. So more random problems. So we're going to do in no particular order. I wish I had organized this into easiest to hardest, but that's okay. Keep you on your toes. So we have 3x quantity power 5 over 81 is equal to 96. Now, we could sit here and multiply the 81 to both sides, but let us not do that. At least the problems I make, I try to avoid tedious computations like this one. It's very unnecessary. So instead, I'm going to leave it as 81 to both sides. Recognize the 81? It's probably base 3. We probably want to change it to base 3, right? Alright, so we have 81 times 96. 96 is kind of an unfortunate number. It's not repeated multiplication of the same number, but at least the 81 is. So 81 is 9 times 9. Each 9 is 3 squared, so it's going to be 3 to the power of 4. I think there's a 3 in there, right? We're trying to match the 3's as much as possible. So how many 3's are in here? There's 3 3's in here, and then 2 3's in there, so it's 32. Okay. We're going to distribute the left-hand side, property of exponents. There we go. What do you know? This is 3 power 5, 3 power 4. If you combine those, that's 3 power 5. So why not cancel that from both sides? Sure enough, we will. Cancel, cancel. X power 5 is equal to 32. Break it down, right? It's 32 to the power of 1. You could change that. You can rename that into base 2. It's just 2 times 2 times 2 times 2 times 2. So 2 to the power of 5. So, in conclusion, since the exponents match and they're not even-powered exponents, we can cancel those. So therefore x is equal to positive 2. Good to go. Next problem up, we have the cubic root of 27 cubed all over 8 is equal to 3a minus 12. Not particularly difficult. You can see that this is the third root. We can distribute that one. Oh, not distribute. We can apply the root to that. And then these ones we already know are very familiar to us. So the 27 is 3 to the power of 3. The 8 is 2 to the power of 3. Everything is exponent 3. What do you know? And don't forget, all the cubic root does is it just takes the third of each exponent. So reviewing a little bit from another time. Another time being yesterday. But if you're a VOD watcher, who knows? If you recall the radical with the index of 3, you can change that into 1/3. Exponent in terms of the translation of radical notation into fractional notation, and we just use the distributive property of exponents. So that is equal to 3 to the power of 1, 8 to the power of 1, and then 2 to the power of 1. No need to worry about plus minus shenanigans. This is odd on the bottom, odd on the top. Don't forget this thing though. Copy paste 3a minus 12. Alrighty then, we have cleanup step. This is going to be 3/2 a. Let's have some semblance of order, right? Move this up. So this is going to be 3/2 a is equal to 3a minus 12. Add 12 to both sides, subtract this from both sides. You're going to get 3 over 2a is equal to positive 12. Multiply both sides by 2/3. So in finality, we're going to get a is equal to 4 times 2, which is 8. Lucky number 8. Alright, so that problem wasn't particularly difficult. So we're good with that one. Then moving on, we have 6 to the power of 8, and then it's going to be multiplied to x to the power of negative 3. Favorite negative exponents. And then we have x to the power of 1 times 9 to the power of 4. Always take a quick survey, to have some sort of plan of attack. Make a few notes. We have base 6, which is very awkward with a base 9, because base 9 we know only consists of 3's. but base 6 consists of the prime numbers 2 and 3. So break it down. And this one we can simply move it to both sides by multiplying x to the power of positive 3 to negate that and therefore consolidate it with this one. So again, multiplying both sides by x to the power of 3 will clear this from left hand side, and then multiply this. Add the exponents, it becomes exponent 4. Same exponent, same exponent. We could probably factorize that. Is that the move to do? No, I'm going to choose not to do that. I will instead distribute this exponent to each of those. So distribute. Oh, you know what? Maybe I'll show both roots. But in all honesty, which method would I have chosen? I'd probably just have done this one. I would probably apply the fourth root to both sides. Yeah, so if I apply the fourth root to both sides, we're going to get 2 times 3 to the power of, what's a fourth of this? It's just 2. I'm not going to write 4 this time. And then you apply the fourth root there. Exponent 1. Be careful, we're applying function to here. This one becomes, transitions from even to odd, so you have to put plus minus for absolute value. Apply the exponent, 3 squared. Oh, okay, so this doesn't look too bad at all. So distribute the exponent, might as well. Cancel that from both sides, please. We have positive 4. We have we have absolute value of x. So x could be plus or minus 2 squared, which is 4. So that's the way I would have done it instinctively. Well, not instinctively, but that's my preference of strategy. But there are other avenues, of course. Depending on your brain, whichever one you find more useful. Okay, so we can split this. We're still going to split that, of course. That's going to be 2 times 3 to the power of 8. Copy, move this to the other side still. So we're still going to multiply both sides by x cubed. X power of 4 times 9 to the power of 4, which becomes 3 squared, parentheses 4, so we can distribute that, thereby getting 3 to the power of 8 to match with that one. But first, distribute. We have 2 to the power of 8 times 3 to the power of 8 is equal to, copy paste. This one, of course, cancels perfectly with that one. And we have the 2 to the power of 8, x to the power of 4. This one is the base. We don't know what this is. This is a known exponent, and this is a known exponent. So we can manipulate that just a little bit to get 2 to the power of 2 times 4. I mean, not times, to the power of 4. Because if you distribute this 4 exponent to this exponent, you get back to the 4. So that's how we're going to do it, and the reason why we're doing it this way is to match this exponent with that exponent. So don't do this. Don't say x is just equal to x squared. You will have lost one answer because this is even exponent transitioning to odd exponent. So you have to put plus or minus. 2 squared, which is 4. Same answer. So we're good to go. And just, again, just as a side note, the reason for this particular situation is this nonsense. If you have x squared and you're taking the square root of that, you have to report plus or minus x. But we already explained that in the previous situation, so let's not dwell too much. Next problem up, we have 2x minus 6 quantity to the power of 4, and then that is equal to 36 to the power of 2. So always watch out for those even powered exponents, because oftentimes they hide 2 answers or more. So what do we do here? Best strat, I'll probably just manipulate this one. Let's change the 36 because I've already memorized that's 6 squared. Why are we doing that? Because we're trying to match the exponents. Why are we trying to match the exponents? Because we don't know what the base, we can't match this base. We can't match an unknown base with a known base. So we can try to match exponents. But as a side note, remember, we're only doing this because at this point we're assuming that these problems are designed so that they will get you proper solutions, and these are not log type problems. Again, this is just stemming from having covered only the exponential rules. So you're not going to get nonsense like 3 to the power of 2 is equal to 4 to the power of x or something. This one, again, you need logarithms. We're not doing that. So here we are. Copy paste that to the power of 4. Distributive property of exponents. We have successfully matched the exponents, but they are even powered exponents. So when you consider matching this one with this one, you have to put plus or minus. So absolute value of 2x minus 6 is equal to positive 6. In order to drop the absolute value, you can consider the situation that it's negative or positive. So let's do negative first, or let's do positive first arbitrarily. So 2x minus 6 is equal to 6. Add 6 to both sides. X is equal to 12 over 2, it is 6. So done with the positive scenario, and then now with the negative scenario. So we have 2x minus 6 is equal to negative 6. Subtracting 6 from both sides, adding 6 to both sides, we get 0, so x is equal to 0. 2 answers. Let's double check these answers. Is 6 good? 12 minus 6 is 6. 6 squared. No, I'm sorry, not 6 to the power of 4, and then this one we already manipulated to 6 to the power of 4. So this answer, consistent. This one's a lot easier to test. We have 0 minus 6, which is negative 6. Negative 6 to the power of 4, the negatives cancel. It will match this one. So this is also good. Nice. Alrighty. What else do we have? Is that it? Alright, moving on to more problems. Where again, we're not trying to incorporate quadratic problems here. Oh, let's do this one. This is pretty fancy. Now recall this one being kind of fancy. So we have 3 to the power of x, familiar base, right? Is equal to 3 to the power of x minus 3. Close parentheses times a very weird x. So this is the problem that we have. It's kind of strange because at this point we haven't encountered something like this quite yet, but it's not going to be too bad. So we have base 3, we have base 3, we have base x. So maybe we're supposed to match the exponents. The exponents are mismatched, and they have unknowns in the exponents as well. So that's wonderful. What can we do in this situation? Well, what we can do is there's not much to do with this one because 3 is already prime. There aren't any numbers to mess around with on this exponent. So this one we will leave it alone. This one is the one we could probably do something because we have exponent minus exponent. So we can change this one. We can change it into a division situation. So, ooh, that's not what I want. So we can change it into 3 to the power of x over 3 to the power of 3. Copy paste that. This is still multiplied to this. There it is. It looks rather strange. Well, this one is the exact same thing as that one, right? And this is multiplication. So for the sake of visual clarity, since this is multiplication, I'm going to multiply this up there, okay? Don't forget, anytime you have a multiplication of a number, you can always force it into fractional mode. Once it's in fractional mode, you multiply top to top and then bottom to bottom. So for visual clarity, I would not have done this if I'm just doing this by myself, but for visual clarity, the numerator will look like that, and then the denominator will look like this. So there we are. This is technically over 1. We can cancel the 3 to the power of x from both sides. Is that a safe move to do? Let's assume it is for a moment. So you can cancel this one from the numerator with that one from the numerator to get 1. So 1 is equal to x over 3 cubed. Solving for x is equal to 27. So we are done with the problem, assuming that this move is okay to do. So is the move okay to do? That is the question. Well, it should feel somewhat familiar. So if you're doing a problem like 3 is equal to 3x, is that not analogous? We have a factor on one side. It's technically 3 times 1, and then we have 3 times x on the other side. So this is a constant. This is a constant. You can divide both sides by 3 to cancel it. So divide by 3. Divide by 3, so x is therefore equal to 1. And then that is safe to do, right? But is this situation the same as this situation? Not quite, right? Because we have some sort of unknown value in the exponent. So maybe there's a nuance that we seem to be missing. I will show you a situation where it's not safe to do it. So if you have x, I'll just put the 1 just for illustration purposes. So you have 1 times x is equal to 3 times x. We run across something that's a bit of bit maybe problematic. So let me change this to x minus 1. So when you're doing a problem like this, actually let me clear this. Let's not put this one. I just want to illustrate something a little cleaner. So if you had a situation like this, we have thing in parentheses times x, and then we have thing times x. So can we cancel x from both sides? So cancel x and solve. And then we're going to get x is equal to 2. Is that a safe thing to do? Yes and no. It's safe if you acknowledge one factoid. So in order to cancel the x from both sides, you would have to say, oh, x cannot be equal to 0 if I'm canceling them from both sides. So therefore, you reach this answer if x is not 0. But in order to get the full answer, I guess, you need to, my suggestion would be to move everything to one side and factor. So here's the answer you will have lost if you simply cancel this x with that x. So subtracting this from both sides, we get 0 is equal to, oh no, this is quadratic. It's not what I intended. But that's okay. So minus x is distributive property. And then we're going to be subtracting this from both sides, so it's minus x. So 0 is equal to, combine these two to make minus 2x. We can factor out the x from those two terms. It's not the goal of this of today, but that's why I'm going to rush it. So we have this one. According to zero product property, there are two ways in which we can generate the 0. Number 1 is the first one we've already acknowledged. If x is equal to positive 2, this becomes 0, and then 0 times anything is 0. At least for now. If we have a definite value, this is a definite value times 0, we'll get you 0. So that's the answer we got before. But this one could also be 0. And that's the one that we excluded last time when we canceled x's from both sides. So as you see, there are two answers. X is positive 2 and x is 0. So don't lose those answers. But this is just a tangent. We're going back to this particular question. Can we just simply cancel the 3 to the power of x from both sides? And in short, the answer is yes, because as long as it's not equal to 0, so as long as provided 3 to the power of x is not 0, we can safely cancel it from both sides, because you can't divide by 0. But anything else, you are pretty much good to go with. Okay? But this lies on another thing, exponentials, right? A different type of exponentials. Do I want to answer this question? Sure, why not? Let's answer it in brief. This is a bit of a tangent, another tangent, okay? So if you're watching VOD, you can just skip this portion. So can 3x ever equal to 0? Well, if you take describing limits, okay. Well, if x becomes a larger value, then you get 3 to a very large value. I'm going to represent that large value with infinity. But please, infinity is not a number. It's not a discrete number. So we have 3 to the power of infinity. This just means a really huge number. So this becomes a really huge number, which is not 0. So we can't get it to become 0 by increasing the value. So what if we decrease the x value? What if it's a negative huge number? Well, now we can kind of incorporate the rules we learned before. Exponential rule, it becomes 3. You send it across the fraction bar. So 3 to the power of positive infinity under 1. This becomes a really big number. We can represent that as an idea by writing infinity. So if we divide 1 by a huge number, it's practically 0, but it's never 0. So we approximate at 0 if we take the limits, but it is never truly 0. So can this ever be 0? No, it can never be 0. So long story short, it's safe to cancel those out because they can never be 0. So we get to here. You multiply both sides by 3 cubed. Solve for x. X is just 27. As an alternative strategy for this particular problem, let me clear this real quick. Again, as an alt strat for this particular problem, you can actually multiply both sides by 3 to the power of positive 3. So when you distribute that to both sides, you can get 3 to the power of 3 times, copy paste, is equal to 3 to the power of x minus 3 in parentheses times 3 to the power of 3 times x. This is okay to do because you can multiply in any order you wish. Commutative property. Alright, so once we reach that particular stage, don't cancel this because that's undoing our prior work. So we're going to do this one times this one. All you need to do is add the exponents since base matches base. So negative 3 plus 3 gets us 0. So we get 3 cubed, copy paste, 3x. Again, this is reliant on dividing both sides by this one, but if you do some visual rearrangement, it might become more obvious. So again, all I did was I swapped those two because you can multiply in any order you wish. So you see this thing is times this quantity, and that same thing is times that quantity, so these quantities must be the same thing, barring 0 shenanigans. So this is never 0, and this is never 0. So we still need that idea. But let us cancel. So cancel this with this one. X is equal to 3 cubed, which is 27. So we're also done with that one. Brilliant. And moving on, doing some more problems. We have a to the power of, and let's put some goofiness. Let's put some radicals in our exponents. Let's go to a to the power of a, and that is quantity to the power of 1/4. So don't be intimidated by the amount of symbols. Just stem from the basic principles. Take a quick survey, please. We see that this is base A, this is also base A, so we can match the bases, drop the bases. Exponents must be equivalent, but we got to distribute this junk first. So use the distributive property of exponents. We're gonna get. I was considering something. You could actually just cancel these directly because the bases match. Drop the base. Distribute. So if you're comfortable combining your steps, let's do it. Here we are. Multiply both sides by 4 to clear this coefficient. So times 4 is 8. Keep the root a. Times 4 is 1. Keep the a. So here we are. It looks kind of gross. There are multiple strats we can use. This is the one we didn't, again, really cover. You can square both sides of the equation. Just be aware, though, it could be getting rid of negative values, but we're going to ignore that for now. So 8's distributive property of exponent. So 8 squared is 64. If you square a radical, that's the inverse, so the squaring undoes the radical. Or if you prefer, instead of writing root a, you can write a to the power of 1/2. If you square that, distributive property of exponent becomes a power 1. But don't forget, a cannot be a negative value, so make sure you consider that later. So we get a, so we make note, a can't be negative. Otherwise, it'll break your function at this location. Alright, so if we square this one, alright, that's what we have. Let me shrink this part because it's kind of confusing. We'll put it right here. So that's what we have at the moment. Can we just cancel a from both sides? We just literally just went over that. You are going to lose an answer. If you cancel 1a from this side, 1a factor from that side, you have to acknowledge that a could be 0. Otherwise, it'll screw things up. So this is going to be one of our answers. And then, of course, the only thing that remains is a on the right side and 64 on the left-hand side. So a could be 64. So 2 answers for the situation using the strategy right here. But again, we're going to avoid the strategy for now. And yet I keep using it, right? That's okay. So this one, rather than using that particular strategy, I'm just going to change that one into the fractional exponent. So a to the power of 1/2. Copy paste the 2. Copy paste the left hand side. Oh, we should have multiplied both sides by 4. So times 4 to right hand side clears that, and then times 4 converts that into 8. Now here's where things become a little more mechanical. We're going to divide a to the power of 1/2 from both sides. So just to show a little bit of work. Cancel, cancel. Again, assuming I think we have to acknowledge that a cannot be 0 by doing this, but more on that in a bit. So what happens here? Well, this is exponent invisible 1. We need to do subtraction of the exponents, so 1 minus 1/2 is just 1/2. There we go. And then finally, do we have to use... oh, you know what? We can change this 8. I guess it might be a little weird though, but we can, this is technically 8 to the power of 1. We can't necessarily match the bases because we don't know, we can't match with what we don't know, but we can try to match the exponents. So 1 is not quite matching 1/2, but we can kind of mess around with it because 1 is simply 2 over 2, right? Let's show the steps. And I chose 2 over 2 and not 3 over 3, for example, because we want to match the denominator on the right hand side. So 2 over 2. But you can change that just a little bit by bringing out the 1/2. So it becomes 8 to the power of 2, parenthetical 1/2. Because, again, 1/2 times 2 takes us back to 1. And then now that we have successfully matched the exponents, can we conclude that the bases are the same thing? Yes, because this is a positive number. We have to say this is also a positive number, so it has to be 64. So we are done with that, but again, we lost something along the way. We have to acknowledge that a is not equal to 0, because that's how you can cancel this safely. But as you saw from the previous root, a could be equal to 0. So second answer. That seems kind of illegitimate, right? It seems the first strat was superior to this particular strategy, but some strategies have pitfalls, and then other ones have more robustness to their answers. All right. Next we have 2 to the power of a, parentheses power a, and then that is equal to 16 to the power of 16. When I'm designing problems, I like to repeat numbers just to make it look intimidating, but don't be intimidated. It's a new face, it's a new mask, but it's the same underlying face pretty much. We have base 2, base 16, surprise, surprise. Please change that to 2 to the power of 4. Distribute the exponents, so we have 2 to the power of a squared. That's kind of awkward. Distribute the exponent. Alright, same base, same base. This is a safe situation where we just drop the base, match the exponents. So a squared is equal to 64. So you can take the square root of both sides if you are comfortable with that strategy. But again, square root of a even powered transitions to odd powered. You have to put plus or minus 8. And then we are done using that strategy. If we don't have that particular strategy, you have to match the exponents as best as you can. This is going to be equal to 64. Again, you can't match what you don't know, so you have to match what you do know. So this is exponent 1. 64 is 8 times 8. We have successfully matched the exponents, but because they are even powered exponents, you acknowledge that this one could be plus or minus. So a could be positive 8 is the first answer. It could also be negative 8. Reasons why we're covered in a different stream. Good to go. Next up we have square root of a to the power of a squared. Isn't that fun? We knew you like exponents, so we put exponents on your exponents. So here we go. We have this one, and then we have a to the power of 3a. That itself gets squared. Fun times abound, but you can already see where this is going. This is base a, this is base a. Right? Oh, actually there's a note I want to make about the previous problem, but let me finish this one first. Hopefully I'll remember. Here we are. Where do we begin? Again, the bases are already successfully matched up. It's this awkwardness This thing, we should probably distribute the exponent. We should probably change this to fractional exponent. So it becomes a squared quantity to the power of 1/2 is equal to distributive property. You only need to distribute it to one factor. Okay, so don't do this. This is the wrong answer. So don't do 3 times 2 and then 2 times a. That is the wrong answer. This is just one term. So you multiply the constant value, known value, you just multiply to the coefficient. Okay, so just to keep things out of confusion. So there we are. This base matches this base, but we should probably distribute this exponent as well. This is half exponent, but remember, when you're distributing exponents, it goes to the coefficient 1 in front. So it's just 1/2 a squared. It is not square root of a squared, so that is the wrong. That's the wrong resolution, so don't do that. So again, this situation is analogous to this situation. So when you have that, you just distribute the 1/2 to the 3. You don't take the square root of the 3. Exponential rule. So let me copy paste this one. So we do arrive at this situation where this base matches this base. Can we just drop the base? I say yes. So let's drop the base and say the exponents are the same thing. Maybe there's a nuance there, but we'll think about it afterwards. So dropping the bases and matching the exponents, we have 1/2 a squared is equal to 6a. So if you cancel 1a here with 1a there, you will lose one answer. You will lose the a is equal to 0 answer. If you bring things to one side, let's do the standard route. We're going to move everything to one side, and we're going to get 0, and we're going to use 0 product property. Let's transform this. So moving everything over to one side, we're going to get a squared minus 6a from this side, and then minus 6a from that side. It's equal to 0. So anytime you reach this particular setup, if you can factorize one side, you could just use 0 product property. We'll factor out a from both of those values. And yeah, that's it. So we have 1/2 a minus 6 times a is equal to 0. So two candidates by which we can generate 0. So this could be 0. Easy setup. This one could be 0. Two answers. So a is equal to 0. Or a is equal to 12. Two answers. We should be good to go. I know I'm probably conflicting with one of my prior statements made in previous streams. I had said that I don't like 0 to the power of 0. Most people would say it's 1. Some other, depending on what practical purposes you are trying to resolve, it could also be undefined, depending on what you believe in, or what's more practical. Let me move this. Yeah, so this is the thing of contention. Is 0 to the power of 1 or 0 to the power of 0 undefined? It just depends. In the situation, if we keep this answer of a to the power of 0, then this one is actually a 0 to the power of 0, which is equal to also 0 to the power of 0, which, you know, if it's undefined, then it's hard to say that's going to be true. So in this situation, if you keep this answer, it's because whatever class you're taking, you would report this answer if they accept that 0 to the power of 0 is 1. If they don't accept it, then you won't report this one. But I think most people, again, would report both answers. So report 0 and 12. Moving on. Next up we have, that's a quadratic problem. I'm going to skip that. Okay, that's okay. We have square root of a, quantity, to the power of a minus 6. And that is equal to a to the power of 4. Standard situation. Base a, we should probably translate the radical into fractional exponent like so. Use distributive property of exponent, match the base, and then drop the bases. So exponents must be equivalent, right? So exponents must be equivalent. We'll just speed run that. So half of a minus 3 is equal to other exponent, which is 4. So a is equal to 7 times 2, which is 14. We should be good to go. Right. Can a be 0? I think a could also be 0. Did we lose an answer? I think we lost an answer. Well, let's double check, because my sneaking suspicion is that a could be 0, right? So if we have 0 as a, will it work out? I think so. Oh, no. We're going to get... Okay, it doesn't. Okay, thank goodness. Let's double check, though. So we're going to get 0. Square root of 0 is 0, but we have 0 to the negative 6, which gets to this nasty situation. And no. So don't worry about that. This is the only answer that we shall report. All right. Wait, something doesn't seem quite right. This is an awfully suspicious answer, because square root of 14 is not a good answer, right? Okay. Let me double check the work, because that, again, the answer is kind of suspicious. So this will be a tentative answer. Let me put a question mark, because again, it's highly suspect. It doesn't seem right. Number 1, it's not a typical number I would use for an answer, and then number 2, it becomes an irrational number. This seems... Oh, this could be rational. Okay, never mind. It might work out. Okay, let's just plug it in just to do a quick check. So we have square root of 14, which is honestly kind of terrible. 14 minus 6 is 8. Plug in 14 for a. Again, we're just checking answers. Oh, okay. No, never mind. It seems legit. So we have 14 to the power of 1/2. Distributive property of exponent. So 14 distribute to that one becomes positive 4. It's consistent. Okay, wow. I did not expect to have a weird answer like that. Well, then again, it's been years since I've made this problem, and since I've looked at this problem. But there it is. Should be good. Next problem up. We have 8. So no more a's, unfortunately. If you like a's, no more a's. So we have 8 to the power of 4x over 3. And that is equal to 4 times... I like to use the dot. I don't like putting too many things. Number 1, a dot is more efficient. And then number 2, this looks like a miniature unknown x. So leaving it dot x. Unfortunately, this will lead to conflict with dot product notation. I think most people do this. Alright. But we're not there. So it's times 2 to the power of 2 times x plus 1 in parentheses. Alright. Don't do this now. This is going to be wrong strat. Don't multiply those two together to get 8. This is, again, this is wrong strat. You know, let me put different colors. So again, this is the wrong strat. Multiplying 4 times 2 to get 8 might seem to be the right thing. If you're rushing this, if you're not careful, you can get to the wrong situation. And then you say, oh, bases match up, so therefore exponents must be equivalent. But you cannot do that, because this is exponent 1, Number one, they are mismatched. Number two, the exponents are also mismatched, so you can't do that. Alright, let me show you the situation where you can multiply the bases together. So if this had instead been 4 to the power of 2 times quantity, x plus 1, copy paste. This is a situation where you can multiply this base times this base, and you're going to get 8 to the power of 2, quantity x plus 1. And it might feel like a random, like a new rule, but it is not. It's just simply factoring distributive property of exponents in reverse. So once you acknowledge that this exponent is the same as that exponent, you can factor it out from both of them, and then you will get in the parenthetical 4 times 2 exponent 2 quantity x plus 1. And multiply the innards, you get 8 to the power of 2 x plus 1. Then it's a safe thing to do. So that's why the shortcut rule works. If you have matching exponents, you can just multiply the bases, because that's the mechanic for it. But neither the bases match up at the moment, nor do the exponents match up. But if you already noticed it, this is base 2, right? This is also base 2. So we're just going to change everything into base 2. So this is base 2 to the power of 3. Whoops. There you go. And then that is equivalent to base 2 to the power of 2. There's that. This is base 2 already. And now we just need to perform a bit of a cleanup. So distribute this one and summate the exponents. So we're going to get 2 to the power of 4x. So those cancel. And then we should probably distribute this. So 2x plus 2. And now we can sum those quantities. So 2x plus 4. We arrive here. This is a constant base, so it's safe to drop the base and acknowledge that the exponents are equivalent. Subtract 2x from both sides, so 2x is equal to 4. Finally, solving for x, 2. And we're good to go. And is this a good problem? I don't know. Let me see. Again, I haven't touched these problems in quite some time. So we have 9 to the power of a. We have a unknown value in the exponent, and then we have times unknown value a in the bottom as well. So that's maybe interesting. This might be a legit problem, or it might not be a legit problem. Let's find out though. We have this thing right here. Unfortunately, this is base 9. We cannot match it with unknown. This is base 24, which consists of 6 times 4. Is that a surprise? Maybe. I don't like that split. Let's do 8 times 3. That's much better, because this is base 3, this is base 3, this is base 2. Yeah, I like the split much better. So copy paste the 16 exponent, copy paste the entirety of the left hand side. There we go. Whoa, where's it equal? There. Let me move it. How did it get so cramped? Okay. So what can we do? Let's distribute the 16 to both of those, because we probably want to resolve this nonsense. So we get 8 to the power of 16, and then times 3 to the power of 16 after distributive property of exponents. This is base 9. That is not base 9. I'm just going to change this to... Do we change to base 3, or do we change this to base 9? Is the question. Well, let's change it to base 3. I feel it's maybe reveals more. So there it is. Again, this is just 9, and then you distribute the exponent. A times 2 is 2a. Copy paste. I'm going to arbitrarily shift that to the front because you can multiply in any order you wish. So we have this, and it seems that some things have lined up almost too perfectly. We have base 3, we have base 3. We have 2 times a, which is a 16, right? And we have base a to the power of 2a and base 8 to the power of 16. So that's very suspicious, right? Is this actually a safe thing that we can do? However, it feels kind of mathematically shoddy if we simply report that it looks close enough. So again, this one looks close enough to this one. It's base 3, base 3. Can we assume there aren't any 3's in here? Well, there certainly aren't any 3's hiding within this 8, right? So all the 3's on the right-hand side reside here within the 16. And again, can we safely conclude that this one matches perfectly with this one? I think we can, but let's do some factorization first. So we can factor out the 2a exponent from those two factors, thereby getting that. We can factor the 16 from those two, thereby getting this. And again, it's kind of a... I wish the answer was more robust than this one. Let me think for a moment. That's too nice. Let's not check it just yet. As I had prefaced doing this problem, this one seems like it's going to be kind of willy-nilly. I think I said something like that. Do we have a better... I remember reasoning this out a long time ago. Hopefully I didn't mess up any mechanics. Yeah. That should be correct. And we can split this 16 into 2 as well. So altering this right-hand side. We can visually do 2 times 8 as the breakup. And it's just too nice. We have a here, a there. We have 8 here and 8 there. This 3 matches this 3, and then this 2 matches this 2. Okay, so because of this match game that we are playing, we can say that a is equal to 8. Again, not particularly mathematical robust. Maybe I'll come back to this another time. But I have a feeling that there's a much better way of doing this rather than just saying, oh, it matches up. Things line up too conveniently. But for now, let me think. Should we accept this as is? Yeah, I don't want to dwell too much on this problem. So we're going to accept the answer as is. Maybe revisit it another time. Maybe. It's gone. Too late. Alright. That was the one with the 9 and the 24 in the problem. Let us do... Oh, this is a quadratic problem. Skip the quadratic problem. That is also a quadratic problem. Okay, this one's not a quadratic problem. So we're going to have the 4n minus 12 squared times quantity n minus 3. That's equal to 4 to the power of 5. So this is, I don't know, I have a feeling this is technically maybe involving quadratics. Alright. We'll try to avoid too much outside knowledge for this one. We have, what do we have? We have 4n minus 12 to the power of 2 times n minus 3 is equal to 4 to the power of 5. So this is weird in a number of ways. The first of which we have two bases in which there are unknowns. We have a base 4 here, we have a uncomfortable 5, a 2 here, and a 1. So all these things are mismatched. So that's rather unfortunate. But if you look at this, this is kind of similar to this one, right? Very similar. There aren't any tricks to perform here. There aren't any tricks to perform here, so therefore the whole problem should lie in this 4n minus the 12. And they're both factorizable by 4. So let's factorize and see what happens. We have 4 quantity n minus 12. Whoops, not minus 12. 12 divided, we're factoring out the 4, so 12 divided by 4 is 3. That's not a coincidence, because someone deliberately designed this problem, and that's me. That is I. There we go. So we have this sort of situation. We have a 4 times a thing. We have a base 4. We have a base 4. Exponent 5. But you know, you can distribute this exponent to those two factors. Distributive property of exponent. Again, just to tease this apart, we have this thing like so. So this is multiplication, so you can distribute this exponent to each of those two things, two factors, thereby getting 4 to the power of 2 times n minus 3 squared. So since we successfully distributed the exponent, we can drop the parenthetical like so, and then we have copy paste n minus 3 is equal to 4 to the power of 5. It's looking pretty good. We can divide 4 to the power of 2 from there, divide by 4 to the power of 2, so subtract 5 minus 2 is 3. We can consolidate this base with this one by adding the exponents. So x minus 3 quantity cubed is equal to 4 cubed. The exponents match up, but they're not even, so we can consider them gone at this point. So again, the operation that you can perform is raise both sides to the power of 1/3. But since we successfully matched it, we can just drop the exponents, because again, they're not even powered exponents. So no need to worry about negative shenanigans. So n minus 3 is equal to 4, summate 3 to both sides, and 7. Good to go. Wonderful. Let's run through maybe 5 more problems, and because I gotta go eat dinner. So next problem up, we have x. Ooh, I hope this is a legit problem. It might be one of those goofy problems. Has a warning. So is equal to 3 to the power of 4 times 5 to the power of 4 times 15. What do we have right here? We have this nonsensical, well, not nonsensical, we have this goofy base x, we have unknown base, we have an unknown exponent, so this might be a goofy problem. So here we have base 3, base 5, this is base 15, but you can crack that by factorizing it into times 3 times 5, which we can subsequently consolidate, so let us do that. So we have copy paste is equal to 1 plus 4 is 5, and then 1 plus 4 is also 5. Yeah, that's very suspicious. Since we have one factor here, we have two factors, why not consolidate? Factor out the exponent. So we're going to get Copy paste, and then we're going to get 3 times 5. Inside the parentheses, we factor out the 5. So therein lies the 5. And 3 times 5 is 15. Easy. We have a 5 here. That's kind of awkward. If you see it, you can see it. If you don't, that's fine. Again, this is a goofy problem. We have x and 15. We have a 5, and we have a 1/3 x. We can try to match this to this one as best as we can by using equivalent fractions, because 5, we can get the 3 in the bottom using exponential manipulations, right? So this one, we can rephrase it. That is equal to 15 to the power of 15 over 3. And again, it's too much of a coincidence not to notice. So we have 15 for the matching, lining up perfectly with the x, and we have an x here lining up with a 15 right there. So I feel there's a more robust method somewhere out there, but this is the strat that I have chosen. And like I said, goofy problem. So x is equal to 15, and then we are good to go. All right. No, that's a quadratic. Let's skip quadratic problems again. Too many quadratic problems. Okay, this one we could do. 45 to the power of 25. Please don't calculate that. And then we have 3 to the power of 50. Oh, isn't that a coincidence? 3 to the power of 50, and then we have square root of n. Quantity, power of n. Quick survey, we have 2 unknowns. Oh, could this be another goofy problem? Well, this is base 45, this is base 3, this is 50, this is 25. This one, not too much to do. This is a prime number. We can maybe break up the 50. This is base n, this is base n. We have a radical. We can maybe transform it into 1/2 exponent, which may or may not be useful. I want to copy paste 3 to the power 50. This is the one we should probably do stuff to. So 45 is simply 5 times 9, which, you know, not coincidentally, we can match it up with base 3. So 9, we could break that down with the 3 squared. It's still to the power of 25. I told you, right? Coincidence? So we can distribute the exponent to each of those, thereby getting 5 to the power of 25 times 3 to the power of 50. Nice. Copy paste. I'm just going to distribute that. Alright. So we can safely cancel factor of 3 to the power of 50 from both sides since it's not 0. We get this thing is equal to this thing. Wow, that's weird. Did I? Something doesn't quite seem right. Let me think. It is what it is. Can we change the 1/2? We sure can. Again, we cannot match what we don't know. We cannot match what we don't know, but we could try to do our best. So this one, we could transform it to have a 1/2 in the front. So it's going to be 1/2 times 50. And let's copy paste the the right hand side. Wow, something really got messed up. I have a feeling this is supposed to be 50, right? But let's backtrack just a little bit. So this is highly suspicious. Hey, let me double check my work. So this one splits into 5 times 9. That's correct. That's just copy pasted from the problem. This is copy pasted from the problem. Distribute this one as 25. Yes. This is 50. Yes. Yes. Huh, it does look correct to me. Yeah, this is highly suspicious. Where did things go wrong? Maybe the problem itself is faulty. Interesting. Well, let me think about this. Let us ponder a few things. This is 1/2 of n. Oh, you know what? That's interesting. Can we not visualize if we apply this to n first, right? So we have 5 to the power of 25 is equal to 2, and we arbitrarily select those ones first. Is it safe to do that? It's safe to do it as long as n is not a negative value. So n can't be negative. If n is not negative, then this is a valid thing that we can do. So I'm going to make a note of that right here, putting these little star right here. And can we resolve this situation? Again, this is kind of a goofy problem. And 25 visually works out. Right? Yeah. Let me show why. So if we force jam the check, if we force the 25 just to check the problem, because we suspect it might be true, the 25 actually works out. So 25, 25. This is the square root of 25, square root of 25, which is 5. Again, this doesn't feel particularly robust as an answer, but we'll take it for now, because I gotta go eat dinner, I think. Let me see if there's one more problem I missed. That is not a quadratic problem. And it's also not a goofy problem. Okay, I think maybe a couple more problems. We have 5 to the power of n plus 4 times 2 to the power of n minus 4, and that is equal to 25 power of 4 times 10 to the power of 56. Again, please don't sit there and multiply that out. It's more trouble than it's worth. So we have base 5, we have base 2. Already that should be raising some alarms. We have base 25, which, you know, you can match that up. And base 10 consists of prime numbers 2 times 5. So that's probably the route we're going to take. We're going to leave this alone. Copy paste. So that is equal to, transforming this, again 25 is just going to be 5 squared. Distribute the exponent. 5 to the power of 8, and then right here we have base 2 times 5. And with that result, we can distribute the exponent as well. So times 2 to the power of 56 times 5 to the power of 56 as well. Oh no, this might be a goofy problem. That's okay. So we'll combine those 5s together, generating 64. Okay, well, here it is. We have 5 to the power of n plus 4 times 2 to the power of n minus 4. Copy paste. Alright, so at this point, is there anything we can acknowledge? Well, this is base 2, this is base, I said it backwards, this is base 5. It doesn't have any 2's trapped inside it. This is base 2, it doesn't have any 5 factors trapped within it. This is base 5, it doesn't have any other factors. It's prime, it doesn't have any other numbers trapped within it. This is base 2, it's a prime number, it doesn't have any other numbers trapped within that. So, is it safe to say this one is equal to this one? I think so. But I'm not a real mathematician. So, that is going to be that. And then this one we assume to be lined up as well. So maybe two answers. So minus 4, n is equal to 60, and then n is equal to 60. So that's consistent. Is that robust? I think that's mathematically sound. Again, the idea is this 5 here, this whole thing here has to align with this particular factor, because this 2 here has no 5s embedded within it, and this 2 should also have no 5s embedded within it. So we can assume that all the five factors are residing here and here. Does that seem kind of shoddy? Maybe. I need more regular problems. So that should be good. I said a couple of more, so one more problem and we're good to go. But let me pick a good one. That doesn't look too good. That's a quadratic problem. Alright, I think I have run out of pre-written problems. Okay, that's fine. I've run out of pre-written problems. Or rather, I have one more problem, but it's not the same as the other type of problems we've been doing. This is just going to be a review from the fractional exponents. So again, this is a bit of a far cry from the other problems, but still involves mechanics. So let's resolve this. So we have radical number 1, and then we're going to multiply that to radical number 2. So less narration and more evaluation. Simplification. Okay, so we have mismatched exponents. Wonderful. This is 6th root, and then this is 3rd root. So we can manipulate this one to match the 6th root. We're going to change this to root 6. So I'm going to multiply all those exponents by 2. This is 81 to the power of 2. This is x to the power of 4. And this is y to the power of negative 10. Again, I multiplied all these exponents by 2. Is that the safe thing to do? Well, we have to acknowledge that there might be negative situations. So we'll consider that afterwards. So moving forward, copy paste. So now we have successfully matched up the two radicals. The indices are each 6, so we can combine the innards, so we can multiply this entire inside with this entire inside because of the distributive property of exponents. Here's what we get. We're going to get 81 to the power of 2 times, so fixed number, known value times known value, and then x to the power of 4 times x to the power of negative 5. Leave this a little uncomfortable negative 1. Multiply those straight across, so we have a to the power of negative 28. Not the most gorgeous response. So what can we do? Well, there's a few number of things that we can do. I'm going to pass the negative cross to the other side, and then also this negative to the other side. Right? Yeah, let's do that. Might not be the most efficient strategy. That's okay. So we have y to the power of 28 on the top, and then x power 1 on the bottom. So if you recall, this is still exponent 1. We try to match it up to the 6th, so we can rationalize the denominator. So top and bottom times x power, you bring it up to the closest divisible number by 6, which is just 6. So 5 to the bottom, and then 5 to the top. And that should rationalize the denominator in an efficient manner. So let's do that. I'm going to start messing around with those ones as well. So 81 is base 3 to the power of 4. 4 times 2 is 8. This one right here consists of 3 and 4s, so 6 to the power of, so let me write it down. 36 is there, it's just going to be 6 to the power of 2, it's 2 times 3 to the power of 2, it's 2 to the power of 2 times 3 to the power of 2. So that's factorizing the 36. This one, we're going to resolve it later. X to the power of 5, leave that alone. X power 6. That's perfect. That's what we want because 6 is perfectly divisible by 6. Alright. Let's move everything. You know what, let's shrink everything. Hopefully that's still readable. There we are. So let's start consolidating things and maybe yanking stuff out simultaneously. So the 3's I will combine. So we have 6th root of, and then we have 3 to the power of 10. You know, I'm going to do it after. I'm going to start yanking values out afterwards. So we have 3 to the power of 10. We have 2 to the power of 2. We have y to the power of 28. We have x to the power of 5. And then lastly, x to the power of 6. I feel that's like a wasted step. That's okay. We do what we must to be clear. Alright, so now we consider what can we yank out. 10 is divisible by 6. How many 6's fit into 10? Only 1. How many 6's fit into 2? No whole 6's. So, oh, I forgot to do leftovers. Alright, backtrack just a little bit. So we're trying to take the 6th root of 10. How many 6's fit into 10? 1. How many left over? 4, because 10 minus 6 is 4. No whole 6's fit into 2. How many 6's fit into 28? It is 3 times 6 is 24. So we have 3 6's, no, what did I say? 4 6's, I'm sorry. Because 6 times 4 is 24, and then 28 minus 24 is a leftover of 4. So again, 4 times 6 is 24, and then 24 plus 4 takes us back to 28. So that checks out. This one we can't. That was deliberately set up. How many 6's fit into 6? 1. So we yank out 1. X. This is technically exponent 0, but we'll just put 1. Alright. So at this stage, we have the answer. We just need to clean it up. So 3 times y to the power of 4 all over x. Let me extend this part. Inside the 6th root, we have all that junk. So we have 3 to the power of 4 times 2 to the power of 2 times y to the power of 4 and then x to the power of 5 all over x power 1. This is the cleanest I can make the answer. I don't wish to multiply those out because that's a waste of time. And I think that's it for now. I think I gotta eat food. I'll see you all maybe later. But since it's a VOD, I guess it's irrelevant. That's it for now. Until next time.